All right, here we go. Welcome to video 2.2. We're going to learn today about what is called free fall. Before we do, we need to learn a little bit about what a force is. This is actually the focus of the next chapter, so I'm not going to focus on it too much right now. But basically what you need to know right now is that a force is a push or pull on an object. There's a bunch of different types of examples. You can have the force of Roy or some person pushing or pulling the object. You can talk about gravity from the earth pulling, a ball down, or pulling your, chair down towards the floor, or whatever. You can talk about the force of friction. Anytime two objects rub together, there's friction between them, and that's a force. Resisting the two objects sliding. When you take physics B, you'll learn about the force of electricity. And something that's going to be relevant to us today is the force of air resistance. As you move through the air pushes on you, trying to slow you down. And you feel that anytime you stick your hand out the window when you're driving down the freeway, right? You can feel the air pushing your hand. Okay, so anyway, we're going to talk about more forces next chapter. What I want you to know now is that force is a measure not of how fast the object is moving, but of how hard the object is being pushed. And it says here, if there's a big force on an object, that means it's being pushed or pulled hard. The force tries to change the motion of an object. And this last part is the important part. Please notice that how much force on an object has nothing to do with how fast it's moving. All right, and as a simple proof of that, I want you to stand up right now and push on the nearest wall as hard as you can. All right, so right now you're exerting a tremendous amount of force on the wall, but it's not moving. Okay, so how much force you're exerting has nothing to do with how fast it's moving. All right, so with that in mind, let's talk about free fall. Free fall. An object is in free fall if the only force acting on it is gravity. Okay, and this actually happens 3 times, and this is a little bit weird. All right, a ball which has just been dropped off of a building is in free fall because after you let go of it, the only force on it is gravity. Gravity pulls it down, and so it's in free fall. Now, even if you throw the ball down, it's still in free fall after you let go of it. After you release that ball that you've just thrown down, the only force on it is gravity, and gravity is going to pull that ball down faster and faster. And the weird one is, even if you throw a ball up into the air, it's still in free fall. Because if gravity wasn't there, it would go up forever, right? And gravity is what causes the ball to eventually come back down, right? So all 3 of these examples that I've got here are in free fall. The only difference is the initial velocity. Okay, when you drop something, your initial velocity is 0, right? Starts at rest, and then when you let go of it, it falls from there. When you throw something down, what's happening is your initial velocity is negative something, right? Because when it leaves your hand, it's already moving down, as opposed to when you throw it, when you drop it. Okay, and finally, if you throw it up into the air, then your initial velocity is going to be some positive number, right? Depending on how fast you throw it up. All right, but all 3 of these objects, whether you drop it, throw it down, or throw it up, are said to be in free fall. All right, don't let the word fall confuse you. It does not have to be moving down to be in free fall. Okay, when you throw that ball up into the air right after it leaves your hand, it is technically speaking in free fall. All right, and the reason for that is in all of these examples, the only force on the ball after you let go of it is gravity. And so that's why they're all going to move down faster and faster. Or in the case of the ball that you threw up, it's going to move up, slower, 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 stop, and then come down faster and faster and faster. Okay. So Galileo discovered that all objects in free fall accelerate at what's called the acceleration of gravity. Okay. We're going to use the symbol AG to represent acceleration of gravity. Just so that you know, many books throughout the world will use just a lowercase letter g to represent that same thing. I prefer using AG because it emphasizes the fact that it is, in fact, an acceleration. All right. Now, on Earth, it turns out that no matter what you're dropping, if you drop an object, it will accelerate down at a rate of negative 9.8 meters per second squared. All right. For simplicity's sake, though, we are going to round it, and we're going to use just negative 10 meters per second squared. And that just makes the calculations a little bit quicker. And I know that if in a pinch you had to do a more accurate calculation, you could do so using 9.8. But we're going to use negative 10. All right. I have not done a good job emphasizing this, so let me rewind for a second. This number here that I've just given you, acceleration of gravity is negative 10 meters a second squared, is true for all objects that are dropped on the Earth in free fall. Okay? Now, in class, when I see you next, I'll do a quick demo where I'll show you that in the real world, it's really tough to have this happen, to have an object in free fall. And you're probably picturing dropping a piece of paper or something like that. A piece of paper certainly falls slower than like a brick, right? And the reason for that is air resistance. Okay, so in this class, we are going to have to, or we're going to assume that there's no air resistance in any of the problems, which is frustrating because in the real world there is air resistance. Unfortunately, it's very, very difficult to calculate the effects of air resistance, and that's something that even in the AP classes they do only minimally. All right, so in this class we're always going to assume there's no air resistance. All right, now, sorry, brain, pause, go. Okay, so also you should be aware that the acceleration of gravity is different on different planets. Depending on where you're at, you're going to have a different acceleration of gravity. On the moon, because the moon is a smaller body than the Earth, the acceleration of gravity is only 1.6 meters per second squared. And on Jupiter, because Jupiter is really big, the acceleration of gravity is right around 100 meters per second squared. To be honest, I need to double check that number. I'm not sure that's completely accurate. But anyway, it's certainly definitely a larger acceleration than it is on Earth. Okay, so what that means, what all of this means is, on Earth, if you drop something and there's no air resistance, it will accelerate down at 10 meters per second squared. On the moon, it'll accelerate down at 1.6 meters a second squared, and on Jupiter at a much bigger rate. Okay. At this point, it's probably not a bad idea for you to pause the video here and watch the other link that I've given you, which I believe I've called 2.2b. And that video is of an astronaut, I believe it's Neil Armstrong, dropping a rock and a feather, or a hammer and a feather on the moon, and you can see that they fall at the same rate. And the reason is there is gravity on the moon, but there's no air resistance. Okay, so everything falls at the same rate. Okay, so please keep in mind, this is what I just spent a whole bunch of time stumbling over. Keep in mind that in free fall there's no air resistance. In the real world there is air resistance, but we'll usually ignore it because unless the object is either very light or moving very quickly, the air resistance doesn't have a significant effect on the object's motion. Additionally, like I said, it's pretty hard to calculate the effects of air resistance. So in this class, here's the big deal. In this class, if an object is in free fall, we are going to use the acceleration to be -10 meters per second squared, which means every second the object's velocity decreases by 10 meters a second. 10 meters a second. Okay? So this is probably easiest to see by doing an example. All right, so I'm going to start over here with this example. It says if Roy drops a ball from rest, VI is going to be 0, which is true anytime something is dropped. So what that means is the initial velocity is going to be 0. All right, because you're dropping it, you know that the acceleration is going to be -10 meters per second squared. You know that automatically because it's being dropped. So this means every second the velocity is going to decrease by 10. So after 1 second, the velocity will be -10. After 2 seconds, it'll be -20, -30, -40, -50, and -60. Okay? And this would keep going if our chart was longer. All right, but what this shows you is the ball is going down, that's why the velocities are negative, at an increasing rate. It's going down faster and faster and faster and faster. Okay? Now, in this next example here, same idea, but this time he's throwing the ball up into the air. He's throwing the ball up at 30 meters per second. So when the ball leaves his hand, it's going up at 30 meters a second. So that means that our starting velocity is 30 meters per second. Okay? Now, because he's thrown it, after he lets go of it, the only force on it is going to be gravity. So we're going to have an acceleration of -10 meters per second squared. And so the velocity is going to decrease by 10 every second. Now think about this. When you throw a ball up in the air, when you first let go of it, it's going fast, but then it slows down. And then it slows down, and it continues to slow down until there's that moment at the top where it seems to hover for a second. And at that moment, your velocity is 0 for just a split second. Okay? And then what happens is it begins to come down. So your velocity then is -10, -20, and negative 30 meters per second. And at this point, it's back down to its original starting point. Okay? This is the advantage to using velocity instead of speed, right? Because just by looking at this chart, I can see what's happening. It's moving up at 30 meters a second, up because it's positive, slows down, stops, and then it comes down, right? Because it's negative velocity, it comes down faster and faster until it gets back to its starting point. Okay? In our third example, Roy's going to throw the ball again, but this time he's going to throw it down at 30 meters a second. So when he first lets go of it, the ball is moving down at 30 meters a second, but after he lets go of it, the only force on it is gravity. So it goes down faster and faster and faster and faster and faster. But once again, the only force on it is gravity after he lets go of the ball. So there's your acceleration, right? All three of these balls have the same acceleration. The only difference is the initial velocity. All three of these balls are said to be in free fall. All right, I think that's it. Yeah, so I basically just walked you through this, but it says, let's take a closer look at the chart in the middle where Roy throws the ball up into the air at 30 meters a second. All right, and this is just kind of clarifying some things that notice on the way up, the ball is slowing down. It stops for a split second at the top before coming down, and then on the way down, it speeds up, right? But if you look at this, even though sometimes the speed is increasing and sometimes the speed is decreasing, the entire time it's in the air, every second, the velocity decreases by 10 meters a second squared because the acceleration is negative 10 meters per second squared. So when I see you next in class, we are going to work on problems where the object is in free fall, which means automatically you know what the acceleration is. All right, so this is going to be one of those things we talked about hidden zeros before. Here's a hidden acceleration. All right, anytime the problem says Roy throws a ball or drops a ball, automatically you know what your acceleration is. Okay, so I believe that's it. Please make sure that you watch video 2.2b, the astronaut video. It's only like a minute. And I will see you in class.